Hey everyone, and welcome back to this class, Deep Reinforcement Learning, Deep Learning in Python Part 7. In this section of the course, we are going to discuss another method of solving the control problem called policy gradient methods. We have so far been parameterizing the value function, but it's plausible that we can parameterize the policy as well. In particular, we want to find the optimal policy pi star. At first, this might seem like a weird idea compared to what we were doing before. Recall that our current strategy is policy iteration. We iteratively switch between policy evaluation, which means finding the value function given the current policy, and policy improvement, which means acting greedily with respect to the current value function. We've seen that this converges so that we get the optimal value function, for which the optimal policy is just taking the argmax of this optimal value function. So what would a parameterized policy look like? Well, we know that the policy has to be some kind of probability, pi of a given s. In particular, we can score each action A using a linear model or any other kind of model. And then, as we know from deep learning, we can use the softmax function to turn these action scores into probabilities. This ensures that all the probabilities sum to 1. For a policy to be optimal, it needs to have some objective. This is something you should be used to from machine learning. Most machine learning methods we've looked at start by trying to optimize some objective. If our model is differentiable, then we can use gradient descent or gradient ascent to reach our objective. Because this section is on policy gradient methods, we are of course going to be taking a similar approach with respect to the policy. The big question is, what should this objective be? Consider that we start in some start state S0. As you know, we want to maximize the total return of the entire episode, which is v of S0. Also remember that the value function v is also dependent on the policy pi, so we can explicitly show that by subscripting v with pi. An unfortunate convention is that the letter eta is used for the policy objective, since we've used it for other purposes in past courses. Just remember that eta in this course means policy objective, which we usually call the performance. Note that theta p here means the parameters we are using to parameterize the policy. We are subscripting the policy parameters with p, since the value function will also have a set of parameters which we'll call theta v. The next few steps are unfortunately not straightforward at all. However, the interpretation makes intuitive sense. So if you want to just skim this lecture, that's fine. The important part here is more about being able to implement the algorithm in code so that you have yet another tool for your reinforcement learning toolbox. It can be shown that the gradient of the performance takes this form, which is dependent on the gradient of the policy itself, which is convenient. This is called the policy gradient theorem. What you can do is manipulate this equation by multiplying and dividing by pi. Once we do this, we can see that the summation is actually just another expected value over pi. But the expected value of an expected value is still just an expected value, so we can make it one expected value. What we can further do is use an identity from calculus. The gradient of log f is the gradient of f divided by f. The last step is to realize that q is actually the expected value of the return g, so we can replace that with g itself, since it all goes inside the expected value. Now we have an expression full of stuff we can actually use. G, which is the return we get from playing an episode, and pi, which is our parameterized policy. So what we would do is, we would play an episode, calculate the returns, and then perform gradient ascent. Notice that's gradient ascent and not gradient descent, because we are trying to maximize the total return, not minimize it. In fact, you could do this as batch gradient ascent, because by the time the episode is over, you have all the returns. In fact, this is suggested by the expected value symbol as well. We know from before that an expected value can be approximated by a sample mean. But also remember that TensorFlow and Theano are going to take gradients for us. In particular, we want just one expression we can pass in as the cost to the optimizer. To turn what we have into that form, we realize that g is a constant, so it can be moved inside the gradient. We also know that the derivative of a sum is just the sum of all the individual derivatives, so we can move the gradient outside the sum. And finally, we know that 1 over t is a meaningless constant because it can be absorbed into the learning rate, so we can get rid of that too. And so finally, we have an expression for the thing we want to maximize. Since TensorFlow optimizers only have a minimize function, we can minimize the negative of this. And to be clear, capital T represents the length of an episode, and the index lowercase t represents the tth time step of an episode. Because this involves the sum of returns over an entire episode, this is a Monte Carlo method. To gain better intuition about the gradient ascent update rule, it helps to look at what it would look like if we were to do stochastic gradient descent, or in other words, the update for just one return, one state, and one action. So there are 3 terms here that affect the new value of theta: the return, the gradient of pi, and pi itself. Remember that pi is the probability of choosing an action A given state S using the current policy. First, consider g, the return. We are moving in a direction proportional to g. The bigger g is, the bigger step we take. This is good because we want to maximize our reward. Second, consider pi, the probability of choosing action A. We are moving in a direction inversely proportional to pi. This is good because if pi is small but the return is good, then we can take an even bigger step in that direction. And finally, the gradient of pi is a vector, so that gives us the actual direction we want to go. The gradient tells us the direction of greatest increase in pi. You'll notice that earlier in this lecture I mentioned using an approximation of v of s as well, but so far that hasn't come into play. One common modification of the policy gradient that we are going to use is to add a baseline. So instead of our constant being just g, it'll be g minus v of s, our prediction of the value at state s. The baseline can actually be any function that depends only on s, but of course since we already know about v, it seems the most appropriate choice. We call this difference between g and v the advantage. The reason we want to add a baseline is because it has been shown to have a significant effect on the variance of the update rule. This in turn has been shown to speed up learning. The update parameters of v, of course, just use gradient descent as usual. A natural question at this point is, can you convert this from a Monte Carlo method to a TD method so that you don't have to wait for an episode to end before doing any updates? Of course this is possible, and in reinforcement learning this has a special name, the actor-critic method. It's called actor-critic because we think of the policy as the actor and the TD error, which depends on the value estimate, as the critic. So in the updates, all we do is replace g with the one-step estimate of g. Now that we've gone through the heavy parts of the policy gradient method, let's talk about why you might want to use it. We know that the policy gradient method yields a probabilistic policy. This should be reminiscent of epsilon greedy, which is also probabilistic. However, it should be clear why the policy gradient method is more expressive. With epsilon greedy, all the suboptimal actions have the same probability of happening, even though one might be better than the other. With the policy gradient method, we can model this betterness directly. For example, it might actually be optimal to do action 1 90% of the time, action 2 8% of the time, and action 3 only 2% of the time. In addition, we should keep in mind that states themselves can be stochastic. One of the sources of this randomness is that the state does not give you the full information about the environment. For example, in blackjack, you don't know the dealer's next card, so the optimal action needs to be probabilistic to account for different possibilities. Now let's summarize this lecture since there was a lot of information in it. First, we saw that we can parameterize the policy so that in effect, we get a probabilistic policy using a softmax output. Next, we saw that the objective that the policy tries to optimize is the expected return from the start state. In other words, this is the expected return over the entire episode. We call this objective the performance. Next, we looked at the policy gradient theorem. We manipulated the results of the policy gradient theorem in order to give us a single cost function that we could then input into Theano or TensorFlow, which is going to be helpful during implementation. Next, we looked at a modification of the policy gradient algorithm that uses a baseline, and we call this difference between the return and the baseline the advantage. We then looked at the actor-critic method, which uses TD updates instead of Monte Carlo updates. Finally, we discussed why we might want to use policy gradient methods rather than policy iteration. It allows us to explicitly model arbitrary probabilistic policies when a probabilistic policy could in fact be the optimal policy. This could in turn be because of the fact that the state transitions are probabilistic.